So for the molecule that we have here, we have been asked to identify suitable reagents for its synthesis by using retrosynthetic analysis. So essentially, this is a thought process of where we imagine that we break certain bonds to generate synthons, nucleophilic or electrophilic synthons, and then identify the reagents that would be equivalent to these synthons. So there are a number of positions here that or bonds should I say, that we could consider in breaking. So the best way to start this is to identify the functional groups that are present. And what you see here stands out quite well is that we have an alkyne functionality here. We have an aromatic functionality here represented by AR. And also we have a alcohol functionality here. So where do we start with this process? Well, if we were to consider that we want to be able to buy the reagents or reactants that are going to be involved in this chemistry to make this molecule, we want to identify them as simple molecules that can be easily purchased. Now, if one was to consider breaking the bond between the methyl group here and the alkyne, it still leaves a rather complex looking molecule here, and that would not be easily purchased. On the other hand, if we decide to break the molecule between the carbon and the oxygen here, yes, we have a hydroxide equivalent, but we'll still be left with this fragment of the molecule, which again would be difficult to purchase. On the other hand, one could consider breaking the bond between the carbon and the aromatic group, but anything involved a reaction on a benzene ring introduces its own complexities to the whole synthesis. So we really want to keep this as easy as possible. So that leaves one bond to really consider, and that would be the bond between the alkyne and the tetrahedral carbon here. So we can represent this disconnection by drawing a wavy line through the bond as a thought process in breaking this carbon-carbon bond. So having decided on that breakage, we should draw our retrosynthetic arrow. Now it's very important that this arrow is drawn correctly as such. Any other type of arrow would indicate if it's a straight line with a single head or a single line with a straight a head, it would represent a reaction. This is representing a thought experiment. This is representing not an actual reaction, but a process of imaginary breaking of bonds. So here we can draw our synthons. So our next step here is to identify the polarity of the respective synthons. Okay, so we'll just draw this here. And now we got to assign our respective polarity. Now this involves us assigning either a positive or negative sign to the respective synthons. Now a positive sign would indicate that the synthon is electrophilic, and a negative sign would indicate that the synthon is nucleophilic. Now just taking a look at this synthon over here, we see that the carbon is attached to an oxygen. Now given that oxygens are electronegative, that would tend to indicate that this carbon will be inclined to be electrophilic. So that's not a bad approach to take. So in this case, we're going to assign a positive sign to this to indicate that this is our electrophilic synthon. Given that we have assigned a positive sign here, then it's easy enough to say that the other synthon will be nucleophilic, and we'll do that. Now we've got to justify this. So one way to justify this in the sense that why would this be nucleophilic and why this would be electrophilic? Well, we've identified that this is electrophilic because of the inclined to be electrophilic because of the electronegative nature of the oxygen is attached. And given that if this is electrophilic, this will be nucleophilic. But also, if we refer to our data tables, sorry for the pause there, but I'm just looking for my data tables. I'm going to introduce them here. This is for some common synthons and their corresponding reagents. Under the nucleophilic section of the synthons, you will see that we have something that's equivalent to our synthon here, the alkyne with a negative charge on it, or negative sign, should I say, rather than charge. And this equates to an alkyne group with a terminal hydrogen. Now, alkynes with a terminal hydrogen are somewhat acidic. They're very weak acids with a pKa of about 25. But in the presence of a suitable base, that will remove that proton and generate a good strong nucleophile. In terms of our electrophilic synthon, we can turn the page of the data tables, and here we have a list of our electrophilic synthons. And if we move down to row 1, not row 1, 2, 3, 4, 5, but row 6, you can see that there is a certain similarity. Let me just move this aside to our electrophilic synthon. And in this case, if we allow R1 and R2 to equate to a hydrogen in each case, so here's R2 and here's R1, well then the appropriate electrophilic reactant will be a carbonyl group. Okay, so I'm going to draw in the respective synthons here. And again, we use a retrosynthetic arrow for each of these. So here's we got propyne. Oh, sorry there. Okay, here's our propyne. And for our electrophilic synthon, we can now draw a carbonyl group. And essentially what we have is an aromatic aldehyde. And given that the electrophilic nature of the carbonyl group here has a delta positive on the carbon and delta negative on the oxygen, you can see that it would be a very suitable reagent point of attack for a nucleophile. Okay, hopefully this will help you in your understanding in this regard. Thank you.